In this video, we're going to demonstrate how we can implement a mathematical model of coffee that's cooling from a coffee cup over time. We have the drawing of the conceptual model here. We have heat laws through this constitutive law. We have a final governing equation that we have derived in the last lecture, and where Ts is the temperature of the coffee and T infinity is the temperature out in the open air outside our model domain. Let's go to Python and see how we can do this. So the first thing we need to do when we make a structured model is we write a little information about what this file does. So we could write the file name. That could be cooling mods for modules. We could write who the author is. We could write the course, and we could provide a short description of what the module does. So that could be a module with a function to simulate temperature of coffee over time. And then we finish up with these quotes again. So this means that this first part will not be interpreted as code when we run it later on. We need this model to be solved in some kind of time interval. So let's just say we have a time range and we want the time range to be, it could be a list or it could be a tuple. Let's make it a list in this case. So we have from 0 to 90 minutes. So we give it 90 minutes to cool off the coffee. Then we need some initial temperature of the system. We could call T init. So let's say it is almost boiling to start with, the coffee. We need to define some constants. The air temperature could be 20 degrees. The mass of the coffee could be 200 grams. We could have the surface area of the cup from which heat can be transferred. Let's have some small number here in square meters. We have a heat transfer coefficient. We'll put on units later on. Then we need the model to be solved at some time step. We call it this dt, and well, eventually we will actually solve it at many more positions than what dt indicates, but this will be the time resolution that we will get the output. So let's say we want the output every minute. We will say it's 1. And according to our governing equation, we also need Cp. So we will just use the heat capacity of water here. That would be 4.2. All right, we are now ready to define our model. And we use the syntax def to define a model. Then we type in the name of the function here. And we know that the function would need all these inputs in order to work. So we put them in here as input arguments. T initial, T air, mass, area, H for the heat transfer coefficient, time range, the time step, and the heat capacity. Right. Then we would start this function by telling the user what is the meaning of these parameters. So we just write again here, simulate coffee cooling using solve IVP. Then we could have a line here saying what parameters are part of the model, and we have T initial. Then it's good practice to type what type of variable is this. It is a float, which is the same as a decimal number, and then a description of what it is. Initial coffee temperature, and the unit would be in degrees Celsius. The next one would be the air temperature. That is also a float, and that is the ambient air temperature, also in units of degrees C. We have the mass, which is the mass of the coffee. It is also a float, and we will use units of gram. Then we have the area from which the heat can be lost. That is also a float. So we say surface area of the mug. The unit is square meters. We have H of type float. That is a convective heat transfer coefficient. The unit is watts per square meter per Kelvin. Then we have dt, which is a time step in output, and that is in seconds. Actually, in that case, we want to simulate for a longer time. If it's, let's say it's 60 minutes, then it's 60 times 60 seconds. Then we have the heat capacity. It is also a float, and it is specific heat capacity of coffee, joules per gram per Kelvin. Right, and then we have defined all the parameters. Then we have to type some information about what the function will then return. Let's use these dashed lines again. So the function will return a dictionary with keys times in units of seconds and T with units of degrees Celsius. And we can now close the documentation part. Whoops, let's just get it one in here. So now the user can easily see what is this function doing and what parameters does it contain and what does it return. So that is really neat for any user of this model. Now we have to define the times that we want the output in. So far we are just giving the time range, that is the start and end, and the time step, but we have to make an array of times that we have to put out from this information. So we use the np arrange function, and the starting time would be time range at index 0. The end would be time range at the last index, which is -1, and then we say plus dt because the last step is exclusive otherwise, and then with the time step of dt here. Then we have to define our rates function. So we use the syntax def again to make a function. We could call it rates, or we could call it dy dt. Let's stick with rates for now. And that needs the time and the temperature, which is the state variable in this case. Then it has to return, and that would be returning our differential equation here, our governing equation. So that would be A times H divided by Cp times M times the driving force, which is the temperature of the system, which we call T and is the state variable, minus the temperature infinity, which is the bulk temperature of the air outside. We call this T air in our inputs, as you see here. And M should actually be mass, because that is what we call the input here. Right. Good. A should be called area also. Now we need to make a call that solves this differential equation here. And we use solve IVP for that. Here we need the first input, which is what function defines the change over time. That is the rate function. We need the time span, and that is actually given as an input to the function. That is called time range. We need the initial conditions. That would be T initial, and because the initial conditions needs to be given in a list, and we can see from the input that T init is given as a float here. So we just make it a list by using these squared brackets. And we need to give information about at what times do we want the output returned. But that we already wrote up here. That is called times. So TA eval is equals to times. Let's call the output from solve IVP for res. And then we need to return the output. And when you return a dictionary, which is what we wrote here, we would do, you use the curly brackets here, and then you can give the names of what you're returning and what variable it should contain. If you remember, solve IVP, it gives a lot of outputs, and you can find the time variable in that output as res.t. The temperature output, we call it T. That would be contained in res.y and at index row 0, all columns. Good. Now I think we have a problem here because we have not really loaded the solve IVP function. I can see it's a problem because it's gray. NP range is also gray. So let's just import these functions or these modules up here. We import numpy as NP, and we import the differential equation solver, the solve IVP. That is found in SciPy integrate. Then we write it like this. Let's go down and have a look here. Now solver VP and NP range turned purple. So now we know it's loaded. Okay, so we now have our whole function here. We should be able to run it actually. Let's try to call it down here. So the way that we call our function cool num is we just write the name of it and give the inputs. We have already defined the inputs up here. So we can just write these directly. It will know what to do. We can call the output for predictions. We have to save the content somewhere. Right, so we have to save this file, and what did we choose? The file name. We said it should be called cooling mods. So let's save it like that. Let's see if the file now runs. Seems that we did not get any errors. So let's try to actually plot what's or print what's in this preds. Whoops. Okay, so we get printed the preds down here with the times and the predicted temperature of the coffee. Let's make a plot also. So for that we need to import the matplotlib.pyplot. We will import it as plt. So preds, and we will have the times, and we will plot it against the temperature T. Let's make sure it shows up. We could add some labels also. We do that. And we add the X label also. Good. Let's run the whole thing again and see what comes up. Have to draw it from over here. So here we have the output from the model. Cooling over 1 hour. We reach around 30 degrees. So that looks good. Right. So now we want to make some restructuring of this because we are not interested in calling our function or making the predictions from the same file where we have the code that defines it. So all this information that we have here, we will move that to another function or another file. Let's make a new file. We will call this cool pred. And we have some description of it, what it does. So this file we want to use for making predictions. And 1 sec. We need to load the plotting library, matplotlib. And now we have to save this file. We call it coolpret. Yeah, good. So now we can actually, because we are in the same root, these two files are in the same directory, and that is also our current directory that we're working in. We can, from this file here, coolpret, we can actually import the functions that are contained in this cooling mods file. So we say import cooling mods, and we could even say SCM for cooling mods. So this is kind of the same way of when we import NumPy, we would say import NumPy as NP. Do it like this. And then within this CM, we should now have a function called coolnum. So if we want to make predictions now, we can refer to that function using this code here. And already here you see information popping up about what parameters does coolnum need. Let's just get it here again. So this also comes from this other file where we wrote the documentation here. So that is why it's very handy to write it like this, because then you can actually see what inputs are needed. So we need the initial temperature. So that would be, let's say it's, let's try now that it's 60. We could say the air temperature is only 10. And we could even be specific. What's the next thing? Is the mass. Let's say the mass is 100 grams of coffee now. The area, we'll keep it the same as before. Not a lot. Age, also the same as before. Time range. Let's say that we want to simulate over just 20 minutes this time. And the time step is, whoops, sorry, it's not minutes, it's seconds. How do you know that? Well, that is the unit of our heat transfer coefficients is in seconds. So the time range also has to be in seconds. We just keep the output in 1 second time step. And then the heat capacity, which is still 4.2. We call the output for prets here. So this is all good, but now we need to just make a little change in cooling mods, because now we define all the inputs here. So the input should not be given inside the function or the other file also, because then they will be overruled. So let's remove all this here. Also, we don't want to make any predictions in here. We want to move this out of this file. We want to have it here instead. We have already imported the plotting package here. And we can now run this code, see how it works. And So there was a minor problem with the saving of the file. So when you have changed something in the cooling mods and you have removed all the stuff, you need to resave it, and you could close the file, and now you should be able to run call the module, um, and you can even, when you have made updates to your module, you can reload it using this line of code. You have to import the import lib, and then you can reload it, and then you should get the updated module loaded when you run with new predictions. Let's try again. And here we get the new initial temperature, 60 degrees. So this looks correct also with respect to time running for 20 minutes. And now we can use the model by changing the input. What will happen if we increase the mass of the coffee? What if the initial temperature was 80 and the ambient air temperature was 30? We could try to run this. Let's see what happens. And then we get the updated output from the model. So this is a way to structure your model by separating the function that describes the derivatives itself from the script where you actually call the model and predict the output.